Hi, my name is John Noonan, and this is the design project for MAE 535, where I will be demonstrating the Lorentz Force in this video. And it is a demonstration of how a resultant force can occur when a current is flowing through a magnetic field. And I'm going to be demonstrating this resultant force using a simplified DC motor. I'm going to be demonstrating 4 different cases of this DC motor, and the purpose of the 4 different cases is to emphasize the importance of comprehending engineering design principles when designing engineering systems. So in this next part of the video, I'm going to be explaining the Lorentz force, which is the first equation that I have up on the board. It is an equation that demonstrates how a charge flowing through an electric field and a magnetic field produces a reactant force. Now, in the case that I'm going to be demonstrating here is for a simplified DC motor. We don't have an electric field in that case, so it gets simplified down to the magnetic force equation demonstrated here, where QV is your current flowing through your wire, and your B is your static magnetic field supplied by a magnet. Now, using the right-hand rule, we put our fingers along the line of the current, fold it in the direction of the magnetic force, and the direction of the thumb is the direction that the resultant force is going to be going in. And that is the basic explanation of the Lorentz force. So now I'm going to be explaining the 4 configurations that we have for our 4 different case studies. In the first case study, we have the magnetic wire loop, or the rotor, where the plane of the circle is in line with the axis of rotation. The magnetic field is protruding up from the bottom, and in this case, using the right-hand rule, we'll have the current that'll be flowing along the top of the wire when the current is actually flowing. It'll be flowing along here. The magnetic field will be protruding upward, and using the right-hand rule, the resultant force is going to be this way, causing a clockwise rotation from the left side, clockwise rotation of the rotor. Now in the second configuration, I'm going to be moving the magnet over to the right side, where the magnetic field lines are now protruding left. Now in this case, when using the right-hand rule, the current is going to be flowing this way when there's connection through the wire, but it's going to be parallel with the magnetic lines, and thus no resultant force will happen, and thus no rotation of the rotor. Now in the third case, I've designed a completely different type of rotor, and what it is a rotor to where the axis of rotation actually protrudes straight through the center of the circle and perpendicular to the plane of the circle. So in this case, we'll have a current flowing through when it's connected. When the current is connected here, current will be flowing through in this direction, and following with the right-hand rule, flipping over, curling the fingers in the direction of the magnetic field, and the force will actually be going that way. And same thing will be happening all around on the rotor. But there will be no resultant rotational force out of it because the configuration is incorrect. And then in the final configuration, what we'll have is moving the magnet over to the right side here, and the current will be flowing along it here, putting the fingers in the direction of the magnet, and curling the fingers will give you a resultant force here. But again, no rotation is going to happen in this case because there's no kickstart in order to make the motion happen. Okay, so in this next part we're going to be demonstrating the first case. So I've hooked up our battery supply. We have our first and second case rotor in place, and we have our magnet. Now we don't have any starting motion, so there's not going to be any motion yet, but once we get this in the right configuration here, get our motor kicked off and going, and voila! Hey, sparks and everything. Go baby go. Woo! Alright, and And that is a demonstration of the first case of a simplified DC motor. Moving on to our second case, where we take our magnetic field and we move it over to the left side, and nothing. Even though we already had starting motion, the lines, no, it died. Yeah. Even though we had a little bit going there, probably because some lines of magnetic flux were managing to interact enough to keep it moving, it eventually died. And that's because the magnetic field lines and the direction of the current, in the cases where the DC power is flowing through, are parallel with each other in case number 2. So here we have our third case configuration, and this is where the axis of rotation protrudes through the center of the rotor and is perpendicular. And as you can see here, I tried to kick it several times and it gets sparks. I got sparks going, so that's cool. But we're not getting any sustained motion. It always dies out. Yep, but we are getting energy flowing through, so it's all built correctly, but it's not configured correct. The design of the motor is not correct, so we're not getting any motion. Now, going into our fourth case, where we have our magnetic field coming in from the side, and we'll give it a little bit of kick here. Still nothing. Alright, last part, the results, putting it all together. So here we had our DC motor, our case 1, functioned great. We had lots of motion, lots of sustained motion all the way around, and sparks, so that was good. In our second configuration with our magnet to the side, we did not have sustained motion. As we expected, those lines were parallel with each other. And then in the third and fourth case, which were just complete wild cards cases, we didn't have any sustained motion there. And this was all really intended for a demonstration of the Lorentz force, but then also more importantly, the importance of comprehending engineering principles when designing these types of systems in the engineering field. And that's all I had, is our simplified DC motor. Lots of fun. MAE 535 rocks.